Hello again. How's everybody doing? We're all struggling through this. Okay, so let's get started. Now we're going to talk about paired samples, tests, and intervals. These will be like, this would be a paired T test or a paired T interval. All right, so I'm starting with an example. All right, and I did put this instructions. So if you want to pause, you can actually load this data into StatCrunch. I already have it there. So by getting into StatCrunch and hitting data load, share data sets, and then looking for this name, and then you can pull it up. So you can run it too. All right, so here's this data, and this is the example. Even though switching lanes and ice skating seems fair, at the 2006 Olympics, some fans thought there might have been an advantage to starting on the outside. So I guess, like, you know, you're in a heat, it's just you and one other skater, and at the beginning of the race, you're on the left, she's on the right, and then at some point you switch, and then, you know, you're on the other sides. All right, so so some people thought there might be an advantage to the outside. We're going to look at this race. This is a 1,500 meter race. There's 17 pairs of women, so there's 34 women. Actually, there's 35, because if you see here, this old teen woman did not race. She just raced by herself. So we're going to ignore her because she's not in a pair, but we have 17 pairs of observations. So this skater is Zhang, that's here, raced with Namoto. They were on the same race. So this is paired data. And what we want to know is, does this data indicate that there is an advantage to either lane? So we're going to check, this is going to be a two-sided test, because we're interested in if either side is an advantage, all right? So what's the setup for a paired t-test? All right, so this is different than independent t-tests. So here I have one population, and in it are all the possible pairs. All right, so you can think of this as being possible pairs of skaters. All right, this is a subset. This is a sample. This is what we have. We have a sample of 17 pairs of skaters. All right, but you can think in this 1,500 meter race, I could have, you know, there's all sorts of people that could possibly win or not, or possibly make it, and then they're in these heats. Okay, so what I want to know, so these pairs, so each observation, so I have, like, this is a pair of skaters, so for each of these pairs I would have two times. You know, I have time one, this is, or let's call it time left, call it time, put a little L down here, time left minus time to the right. All right, so where the left is just where they start, the right is where this other person started. So each possible set of times, oh, actually I just need a comma. There's this time left and time right, so there's this time. And I'm interested in the difference, because we want to know if there's an advantage. So what I'm going to be looking at, this is the comma, by the way, comma, is I'm going to be looking at the difference in these times. All right, and we're going to use, and so the mean difference, so this is mu d, this is the parameter of interest. This mu d is the mean difference of all possible skaters in this race. In the 1,500 meter ice skating race. All right. All right. So what does that mean here? All right. So that would mean, all right, so I've got the left minus the right. All right. So this is how much, so if this was positive, this would be how much more time it takes in the left lane than it does the right lane. So this is the average extra time it takes in the left lane. than the right. All right, so again, this is a difference in means. It's the average difference. And mu d is like, so this would be the advantage to the right lane. So if it's positive, it takes more time in the left lane than the right lane. And if it's negative, it takes more time in the other lane. Do not disturb. Okay. All right, so over here, I'm at my 17 pairs of skaters. I'm going to have a mean difference of all those skaters, and that's going to be called D bar. And we'll also have a standard deviation of difference. And what that's going to be is if I look over here, again, I'm going to ignore the first lane because I don't have a pair. But if I look, I'm going to have 17 differences. The first one will be, and we're doing this, so it's not even right minus left, it's inner minus outer. So this will be inner minus outer. Yeah, I don't know which of those. This is the left or right, but either way. All right. So for this one, the time for this Zhang Nemoto race, the difference is going to be 125.75 minus 122.34, and that equals 3.41 seconds. So Zhang took 3.41 seconds longer than Nemoto. And then on the next one, the difference, this is 121.63 minus 122.12, and that equals 0.49. And so that's almost a half second. So this time, Lamb took longer. So this was the longer guy. So Lamb took, this is a negative. Lamb took about a half second longer to finish than Abamova. All right, and etc. I have 17 of those. And so if I took all those differences, here I'm going to do the last one too. That one would be, so then this one would be 116.9 minus 120.77, and that is minus 3.87. All right, this one, Tabata took 3.87 seconds longer than Wolf. All right, so D bar, that is going to be the average of all those differences. So that would be, the 3.41 plus this one's a negative 0.49 plus all the way to the end, plus negative 120.77, and I would take all of that over 17. All right, so that's the average difference. That's what D bar is. And that D bar is a statistic that should be a good guess at what mu D is, which is if I was to have an infinite number of Olympic races, what would happen? All right. So, so that's what we'll calculate, and that's what we're going to use to test if there's an advantage to either lane. All right, so our hypotheses. Our hypotheses are always about the population, and my population parameter of interest is going to be mu d. So these are going to be about mu d, about the mean difference between the inner and outer. Inner and outer. Okay. So my null hypothesis is going to be about that mean difference, and my alternate is going to be about that mean difference. The null is always an equality, and my alternate is always an inequality, which will be less than, greater than, or not equal to some value. All right. And I told you this was going to be a two-sided test because we want to know, is there an advantage to either lane? All right. So is one lane faster than the other? So this will be not equal to. And so if there is an advantage, then there should be a mean difference of some sort. All right. So if this is 0, if mu d is 0, that means on average, neither lane is faster. If it's not 0, this means that one lane is faster than the other on average. All right. So this is going to be, this is our two-sided alternative. Okay, So now we're going to check the conditions. The first condition is a new condition. This is a paired data condition. We need to check, is it valid to do a paired t-test? So in order to do that, I have to have paired data. And so that means I have to have, I have to have one observation in one column that goes with the other. And so since, when I look at this data, that this Zhang, okay, was actually racing side by side with this person, then their times is a pair of measurements for a single race. So my unit is I think they call it a heat. All right. So first heat that has 2 racers in it, I got 2 times. Second heat, so I have 17 pairs of times. All right. So this is definitely paired. So we got 17 races, and I got 2 times, 1 for each racer. So this is paired. Now I have to have independent. This is independence between the pairs. All right. So are the times in the first race? Actually, it's the first race difference in time. All right, independent of the second race difference in time, and so on and so forth. And the answer is yes. There's 2 different. The next 2 people are 2 completely different people. Who knows what the difference in time for those are? So this is yes. So I definitely have independence, and then I have to ask myself: are these 17 races, are they representative of the 1,500-meter event? I would think, yeah, that they're the type of people who would compete in that race. So I think that yes, they're independent. Yes, they're representative. So this is a pretty good sample. Okay, now we need to check the almost normal condition. All right, and in order to do that, I have to have a histogram of, actually, it's of the differences. So here we're going to run StatCrunch, and here are the directions for doing that. And I'm going to do that also in actual StatCrunch. Here we go. All right, so I'm going to click Stats, T-Stats, and this time I've got paired data. And I'm going to put the inner lane in here, the outer lane here. And I'm going to save the differences just to show them to you, but I don't really need to. Here's my hypotheses, mu d equals 0, and we are doing a 2-sided test, so not equal to is fine. And I'm going to look at a histogram, and maybe a box plot, maybe. I always like them both those. All right, so here's my output, but I want to look at that histogram. And here's my histogram. All right. And I got to ask myself, does that meet the qualifications so that the mean is normal? All right. This guy looks normal to begin with. This is unimodal symmetric. So basically, as long as I have at least 5 in my sample size, we're fine. All right. So let's kind of go back and write that up. All right. So, so we got my n is 17. I've got 17 pairs. So so my sample size here is 17. I've got 17 differences. And so that is a small sample. No, wait a minute, actually that's a moderate. 5 to 15 is small, so this is on the small side of a moderate sample. So as long as it's at most slightly skewed, then we meet this condition. And it does. This thing it's unimodal symmetric, so it's not even skewed. So this is great. This looks perfect. All right. So we've met all our conditions. So what that means is those differences in times, those 17 differences in time. Okay, here I'll put n. All right. Those 17 differences in times. All right. Those are going to be normal. That's what this little n means. This means normal. And the mean of those differences should be, the mean of those sample differences should be mu d. So that's the population difference in these. That's my advantage to either lane. And with standard deviation sigma d, which that guy is the standard deviation of all the differences in the population, and then n is my sample size, which is 17, right? And so that's normal. So when I have a normal distribution, I can get a z-score by taking this guy, subtracting its mean, and dividing by its standard deviation. So if I take d bar minus mu d over sigma d over the square root n, I get a z, and that guy, that z, is a standard normal, which means it's normal with mean 0 and standard deviation 1. So that's standard normal. Well, just like in the past, we don't know what sigma d is. So we're going to use SD. So SD is the standard deviation of those 17 differences in time. We're going to use that as an estimate of sigma in this little z formula here. And when I do that, I replace it, I get a t. So that's what I got here. This guy has a t distribution with n minus 1 degrees of freedom. So it's a lot like, so the paired t-test, it's the same, it's equivalent to doing a one sample t-test. When we had a one sample t-test, we took y bar minus mu 0 over s over the square root of n. Well, now we're just, instead of y bar, instead of looking at actual values, we're looking at differences. So it's a b bar. And so my test statistic, we assume the null is true. So we're going to use mu d from h0. That's what mu sub d sub 0. So we've got a subscript and then a subscript of a subscript. So mu sub d of 0. So that means the mu d from h0. Well, that guy has 0. So this guy right here is 0. So then what that leaves me with is d bar over sd over the square root of n. So here's my test statistic. All right. Now in StatCrunch, if you want to run a paired test, you have to have 2 columns of data to do a paired test. So, so that's what we're going to do. So we're going to run it in StatCrunch, or actually we already did. When I got my histogram, I ran the analysis. So here's the output. All right. So this is this mean here. That is the mean difference. That is d bar. All right. So I copied over here. So let's find it. All right. So here's my output from that. This is d bar, all right? And that is the mean difference in times. All right, and that is approximately a half a second. All right, this is 0.499. This is around a half a second longer. And that was inner minus outer, so the inner must be bigger. So it's a half a second longer for the inner lane. All right, so we're looking at that. We got a half a second for those 17 racers is a half a second longer in the inner lane. So it could be, this is, this means there's the potential that the outer lane has an advantage. So maybe on average, for all races, the outer lane is faster. But, this is only 17 races, so I don't know, is that a big deal or not? Is half a second a big deal? In order to find out if it's a big deal, I have to do the test. I've got to look at the p-value. And here's my p-value. And here's my test statistic. So so the test statistic is t equals 0.88. 881. You need 3 decimals. All right, and the p-value is 0.39. 0.3912. All right, is that a big deal? No. Okay. How we ask if it's a big deal is we ask if the p-value is less than 0.05. Is this less than 0.05? No, it is not. So I'm going to have 3 no's. It's not a big deal. It's not significant. So I'm going to fail to reject the null. All right, and let's recall what those was. H0, what those were. H0, UD equals 0, HA UD, and we said, is there an advantage to either lane? So that's a two-sided alternative. All right, so we're going to fail to reject A0. That means I can't reject. So this could be true. It could be that there's no advantage. UD equals 0 means there's no advantage to either lane. So that's a possibility. This is not significant. So a half a second difference on average in the lanes is not that big a difference. So that's not, we expect that kind of thing, all right? And the last one is this data does not provide sufficient evidence that there is an advantage to either lane. All right. So we don't know if there's an advantage or not. We don't really have good evidence either way. So it could be, it could have an advantage, or it may not have an advantage. We just don't know. All right, so let's calculate a confidence interval for that. Even though it's not significant, I want to see what the confidence interval for what kind of differences are possible, or not even just possible, what kind of overall mean differences are likely, okay? So what I'm going to do, once I've created a test, it's very easy to go back and just change it to a confidence interval. All right, and then I get this output. And now I get that all that's the same. I got the same half a second, all those, but now I've got this lower limit. I think I put that in here too. Oh, I meant to. I put the wrong stuff in there. Hold on. Okay, that's better. Okay, so there's my output. And you can see here's the half a second. Here's my standard error. Okay, so here is my lower limit. I know it's hard to see. Okay, so there's my lower limit and my upper limit. All right, so my confidence interval for the mean difference. So this is really, it's the advantage to the outer lane, but it's the difference between, it's the average inner lane minus outer lane time is negative 0.70 seconds to 1.70 seconds. Well, just might as well get rid of the 0, just 1.7 seconds. All right, so what is the interpretation for that? All right, so always I start out with 95% confidence. And then I got to talk about the population and the parameters. So I'm looking at the mean difference in the population. So for the population is like all the 1,500 meter races. For the 1,500 meter races, all of them, not just the ones that we saw, not the 17. The average difference in time is between, all right, so on the lower end I have this minus 0.7. So if it's negative, so the negative means that the second one is bigger. So negative, so when it's on this end, so if mu d is negative, then the outer takes longer. And if it's positive, that means the inner takes longer. All right, so the difference in time, so on this side, So it's possible that the outer takes longer. In between, so the average difference of time is either, so that's 0.7 seconds longer for the outer lane. Right, and what do we got? 1.77 seconds on the other side. That's longer on the inner side. All right, so I've got one, so basically what is possible, so this is kind of reiterating what I had in the test. It's possible that I get something negative, which means there's an advantage to the inner lane, because the outer takes longer. And it's also possible that I have a positive value, which means there would be an advantage to the outer lane. So either one of those. So based on this confidence interval, there could be an advantage to either lane or no advantage is also. So those are all the reasonable values of the difference. But if there's an advantage to either side, at most, according to our 95% confidence interval, it would be 0.7 seconds advantage for the outer or for the inner, or 1.7 for the outer. All right. Okay, we're going to do one more example. And this one, we're just going to do the interval from scratch. All right, so I have, what I have are data from, so many moons ago, I collected data from, I had 2 huge classes of Stat 205 students, and I asked all of them what's their father's age and what's their mother's age. So I put them in this, so these are Stat 205 students, parents' ages. All right, so we're going to see if fathers are older than mothers or not. We're not just going to see if they're older, but we're going to say, what is the average difference? That's what the confidence interval is going to tell me. So I'm going to do a confidence interval for the average difference in age. Of fathers and mothers. Okay, so what are my conditions? First, I have to check. Well, that is so interesting. Confidence interval for the average. Okay, so is it paired? All right, so I'm going to have a father and mother. So my unit is a student. All right, so it's a student. So each row is going to be one student, and it's going to have the father's age and the mother's age. So I'm going to have 2 ages associated with the student. So that is paired. I have pairs of parents. All right, so yes, it's paired. The next one is the independence or randomization condition. All right, so I'm going to, so I have to think about what my population is. All right, so my sample is a bunch of students, 205 students. So maybe my population is, either all NKU students or all Stat 205 students, or, basically it's all the kinds of students that take Stat 205. There's a lot of different kinds of students there. Right. Some majors don't have to take it. So I mean, are we? And I really, maybe I could even say, the ages of these students, maybe I think they maybe represent all NKU students. Maybe. All right. So whether it's representative or not of that, I'm not sure. But I do know they're independent. And when I say independent, right? The father's mother age and the mother's age are not independent. Those are dependent. All right. So if I've got a father that's 80, then my probability distribution for the mother's age is not the same as if I had no idea how old she was. So she's probably close to 80 if he's 80, right? I mean, there's exceptions, but You know, so I expect the mother's age to be close to the father's age. So those are not independent. But the difference in ages for a student, so what I'm looking at are these pairs of ages. So are the difference in ages of the students independent? And the answer is definitely yes. It's like, so if I talk to, you know, one of the students and I say, okay, you know, your family, your father's 5 years older than your mother. Is that going to affect the next student's parents' ages? No, it is not. They're independent, right? So, so I do definitely have independence, and if I pick my population right, you know, I have representation. So that's good. All right, now last condition is the almost normal condition. And again, I have to look at a histogram of the differences. This test is all about the differences only. Once I know what the differences are, I'm uninterested in the actual values. And I'll show you that. All right, so we're going to go to our data set. I shared this one too. This is paired T parents' ages if you're interested. All right, so here's all my data, and I'm going to do a stat, T stats paired, and I'll use father and then mother, and I'll save those differences. We don't need to, but all right, so I've got a histogram. Actually, I do want to look at my histogram and a box plot. I know I keep saying box plot, not looking at it, but it's all right. So, okay, so let's go see what the sample size was. I don't know. It's pretty big though. 84 degrees of freedom. So I've got 84 degrees of freedom. What's my sample size? Think about that. Well, what are the degrees of freedom? This is like a one sample T. So the degrees of freedom are n minus 1. So n minus 1 must be 84. So if I subtracted 1 to get to 84, then n must be 85. So I have 85 sets of parents. All right, anything bigger than 40, we're calling a large sample. So this is a large sample. So as long as it's not extremely skewed and no extreme outliers, so it's just not extreme. But it's not extremely skewed, no extreme outliers. And I would say this is slightly skewed right. Right. Yeah, so I've got 3 bars to the left, 1, 2, 3, 4, 5, 6 to the right. So this is like a slightly skewed or just skewed right. So it's definitely unimodal and maybe slightly skewed right, but as long as it definitely is not extreme. So we're good. This is good. So that means we have normality. Then I can do the test. All right. So for the calculations, again, I'm going to use StatCrunch. I'm going to use stat, T-stats paired. Okay. Let's get this back here. Oh, we already did it. So we did stats, T-stats paired, and then I picked my columns. And so here's my output. Okay, let me just bring this down. Okay, so well, again, what do we got here? I got the mean is 2.46 years. The standard error, which is SD over the square root of n. Like that, 84. My TV might be dying. Okay. So this guy right here, this mean, again, this is D bar. This is the mean difference. All right, so this is the difference in age. This is the average difference in age, or the mean difference in age. And since it's fathers minus mother, this is how much fathers are older than mothers on average. So fathers are you know, approximately 2.5 years, 2.46, all right, 2.5 years older than mothers for these 84 students. All right. And then the standard error, that's SD over the square root of n. And I ran a test. Those are the confidence interval. So let's change this to confidence interval. A little bit better. Okay, that's better. Sorry about that. All right, so here's my confidence interval. All right, so it's so my confidence interval. This is for UD. This is the average difference in age for all parents of 205 students, historical and future. All right, and that is let's see, 1.65 to 3.27 years. All right, so again, this is the average difference in age. So my interpretation, I'm going to say with 95% confidence, and this is an average difference, and it's fathers minus mothers. So this is going to be that fathers, on average, are between 1.65 and 3.27 years older than mothers. Again, this is on average. This doesn't mean that I think fathers are that all fathers are between this much older, this and this much older than mothers. This is the average. So on average, we're trying to estimate how much older fathers are than mothers on average. Well, I don't know what it is, but somewhere in between here. In my sample, it was around 2.5 years. And with my margin of error, I'm pretty sure the average difference for fathers and mothers is in here. All right, I'm going to show you something. All right, so that's not this. All right, so I'm going to do a graph. All right, I'm going to do a box plot. I'm going to do a box plot with all three of these things: father's age, mother's age difference. All right. So I'm also going to add horizontal lines. I want to look at compared to zeros. There they are. All right. So when I'm looking down here, this is the test is completely based on these differences down here. And if you look, the line 0, all right. And remember, this is a box plot. So these are the horizontal lines are the minimum, the first quartile, the median, the third quartile, and the maximum. All right, so this, it looks like 0 is the first quartile. In fact, it says so. All right. So what that tells me is that 3/4, okay, there's a 25% between the first quartile and the median, 25% between the median and the third quartile, and 25% between the third quartile and that maximum. So 75% of the parents have the father being older than the mother. All right. So that kind of gives me, when I see that, I think, okay, well, then probably on average, fathers are older than mothers. All right. And that's what our test or our interval found out for us. It's like, yes, it's somewhere between, let's say, 1.65 and 3.27 years, yes. All right, but if I just look at the father's age versus the mother's age, and this is what I would look at if I was interested in, if I was doing an independent test. So if I look here, I mean, I can see that where this father's age is, all right, that median age, and it's just a little bit taller, you know, it's a little bit higher than the median age for the women, or for the mothers. But if I didn't know that one went with the other, then there's a lot of overlap in this middle 50% of the data. All right, so the box, remember the IQR is the height of that, but the box tells me, you know, what's going on in the middle. Well, there's a lot of overlap here. So looking at this, it wouldn't necessarily say, wow, I'm pretty sure fathers are older than mothers. But when I look at these differences, it does. And so the differences, it makes no difference to the differences how old people are. So here, you know, I've got somebody that's, you know, what's the minimum? Oh, -4. So somebody, the -4, oh, okay, this is looking at the wrong thing. But anyway, so like this person up here, there's somebody who looks like they're like 85 years old. And they're pretty far an outlier compared to the rest of us. So somebody has a very old parent. But that doesn't necessarily mean that their difference is an outlier, right? Because, all right, let's take a look at what this guy is. This guy, he's row 85, he's 87 years old, all right? So that's in row 85. And I look over here and see how when I click that, both of these are pink. So the mother is 82. So I've got 87 and 82. So their difference is 5 years. 5 years is not an outlier. You can see that it shows up on there. So 5 years, that's not a big deal in difference, even though these are, so an outlier in the actual data does not create an outlier in the differences. So the paired T is just, it's all about these differences. We kind of ignore the actual values of the ages, right? So 1.6, you know, it's clear here that 1.65 and 3.27 have nothing to do with the actual ages of the fathers or the ages of the mothers. There's no father or mother near 2 or 3 years old. So it's apparent here. So you got to remember that when you're looking at other things. All right, so based on this confidence interval, does that mean that we have strong evidence that there is that one parent is older than the other on average, all right? And so does this provide me strong evidence of that? All right, so let's say that. Does the confidence interval provide enough evidence that does the confidence interval provide enough evidence that one parent is older on average than the other parent? And the answer is yes. So why is that? And the reason is because both the left and right side are both positive, right? So the entire interval is positive. So all the reasonable values of the difference, the smallest difference in ages is where the fathers are 1.65 years older. And the biggest is that they're 3.27 years older as the fathers. So on both ends of this interval, the fathers are older than the mothers. So then that means I'm, you know, with 95% confident, I think fathers are older than mothers. and values 1.75 years to 3.27 years. So that's the answer here, all right? In the previous example, another way to say this, the entire interval is positive. Also, I could say that 0, the value 0, is not in the interval. And those are equivalent, all right? 0 is not between, here's 1.65, and here's 3.27, and then over here we have 0, all right? So here's my interval. 0 is not in it. The entire, this is, so I think UD, the difference in all parents' ages are somewhere in here. And so 0 is not in there. But when I was looking at earlier, when we did our other example, oops, I went too far. There we go. All right, notice that one side was negative and one side was positive. All right, so 0 is in that interval. So here, if I was looking at this interval and I said, well, does this indicate that there is that one of the lanes has an advantage? Then I would say no, because the entire interval isn't positive or negative. I mean, if the entire interval is negative, it would mean, oh, okay, then the outer lane takes longer. If they're both positive, this would indicate the inner layer takes longer. So because one side is negative, one side is positive, then it means, well, it could go either way. And so in this case, 0 is in the interval. All right, so when 0 is in the interval, all right, or the entire interval is not positive or the entire interval is not negative, that means we don't have enough evidence of a difference. And remember, for this guy, we had a p-value of 0.39. There was not evidence of a difference. All right. So if I want to use my confidence interval to give me information about whether there's a difference or not, I got to think about, is the entire interval positive or negative? Okay. All right, that's all I have. Thanks so much for listening to me, and I hope you guys are doing great. I just wanted to let you know, if you're struggling, that's normal. I'm struggling too. I'm working like a dog to get all this done, to do all my work. And so you shouldn't feel bad if you're overwhelmed. It's normal. So, but we're going to get through it. We only got 4 more weeks of school, and we're all going to make it. All right, you can do this. Take care. I'll have new videos next week, and this should provide you with enough to do for this week. So have a good day. Have a good week.